Hello students, in this video we will solve one example of moment of inertia for an area enclosed between curves y square is equal to 4ax and x square is equal to 4ay about x-axis. So here, these are our two curves. This green is y square is equal to 4ax and the blue is x square is equal to 4ay. So our region is this shaded region. We have to find moment of inertia of this region about x-axis. Okay, so formula for moment of inertia, that is I is equal to integration d square dm. In previous videos, we have seen the formula is integration r square dm, where r is the distance of the particle from axis of rotation. But here we are taking d as the distance of particle from axis of rotation, because when we are solving examples of polar coordinates, there we take r as a radius vector. So to avoid confusion, we will take d for distance of particle from axis of rotation. Okay, so now what is the d for this? So let us take one particle p x comma y in this region. We have to find its distance from x-axis. So this distance we have to find. You can see here this distance is nothing but the height of the particle above x-axis, which is y coordinate. So here d is equal to y, and therefore we get moment of inertia is equal to double integral over a, because we are finding moment of inertia for area. So it is double integral over a. Now d is y, so y square, and dm will be rho into dA. dm represents mass of a small object, so which is rho times dA. Now we have to find limits for this area. So let us take one vertical strip in this region, and we have to move this strip from left to right in the region so that it will cover whole region. You can see to left side it will come up to this y-axis, that is x is equal to 0, and to right side it will go up to this line x is equal to 4a. So limits of x are from 0 to 4a. Now to find limits of y, we have to see how the bottom end of the strip varies. You can see here the bottom end of the strip varies according to this blue curve, which is x square is equal to 4ay. So therefore this blue curve is a lower limit of y, and top of the strip varies according to this green curve, that is y square is equal to 4ax. So green curve is upper limit of y, and therefore limits of y are from x square upon 4a to under root 4ax. So let us integrate this over these limits. X varies from 0 to 4a, y varies from x square upon 4a to under root 4ax, y square rho dy dx. As in this example density is not mentioned, we'll assume that density, that is rho, is constant. And after integrating this, so we get I as 768 upon 35 rho a square. So this is how we can find moment of inertia for this plane area. Now see here we got answer in terms of density, that is rho. But sometimes you may be asked to find moment of inertia in terms of mass of the body. So here let's calculate mass of this region. So mass of the enclosed region M. So here we have to find mass of this region. We know that mass is density into area. So M is equal to rho into A. Now we have same region, therefore limits of x and y will be same. So mass will be rho into, and the area is double integral over a dx dy. This double integral of dx dy gives us area of this region. So when you solve this with these limits, we get area of that region, which is 16 by 3 a square, that is the area of this shaded region, and therefore mass of the shaded region will be density into area, which is 16 by 3 rho a square. So now we got mass in terms of density. So moment of inertia in terms of density is this 768 upon 35 rho a raised to 4. Mass of the enclosed area M is equal to 16 by 3 rho a square. So from here we will get rho, that is the density in terms of mass, which is 3m upon 16 a square. Now put this value of rho in this first equation. So we get moment of inertia I, which is 144 upon 35 ma square, which is in terms of mass. So this is how we can find moment of inertia in terms of density as well as in terms of mass. Thank you.